you. Thank you. Bye.
Next speaker now. Hi, Shreya. Can you hear me?
Yeah, Sandeep, I can hear you.
Shreya, you want to share your screen? We'll just check if it's working out.
Actually, the audio is much better now. So that's good.
No, with the screen. Just see if you can share your screen now.
Let me bring it up.
Yeah, so this is
Is this
good. Yeah. Okay, so it's my great pleasure to welcome Shreya Agarwal. Thank you, Shreya, for making time for us. Shreya did her master's in mathematics from University of Waterloo, and she's a senior software engineer at Google Research, and she's part of this team which has been doing very exciting work on nowcasting and other aspects of using machine learning for weather forecasting. We are very thrilled to have her talk about right now. Thank you.
Hi, everyone? Thanks for having me here. Uh, Hopefully I can keep it within the time frame, and it's late at night there, so hopefully all of you can yeah, don't have to spend too much time on this now. Okay, so feel free to stop me anytime during the presentation if you have any questions. I'm happy to answer any questions, or if there's any questions even later on, I'm happy to dive into it. Okay, so I'll talk a little bit about a project I've been working on for a few years now. So a little bit of a background about me. I joined Google as a software engineer with just a CS background. And weather modeling is something I started doing at Google, learning about the weather. So I'm not a weather expert. I'm not a meteorologist. It's just something, our team has been learning on the job. I don't know how many of you here are, have a more of a background in weather, or more in data science or computer science. But I would say, it's it's not something, even if you have a good background in computer science, I think you can start making some progress in weather modeling, which is great. So we've been doing precipitation nowcasting. I believe what nowcasting is has been covered in the previous talk, or like maybe some other previous talks. But our goal is basically to forecast the weather in the short term, and specifically precipitation, because that's the hardest variable to forecast in general. And especially again in the short term, because the burst of rainfall, it can be quick. It's not like a smooth moving variable like temperature. So you can have convective rainfall, you can have thunderstorms that can last a very short time, and so it can be very hard to pick up some of these variables. Also, nowcasting is very crucial for providing early warnings to users and various agencies. For users to know whether they should leave with an umbrella in the morning, when to leave for home from work, for agencies to provide warnings in case of extreme precipitation to other users of their forecast. So nowcasting is a very crucial element of weather modeling. So with the forecasting models today, a lot of the models, especially the physics-based models, are designed to work better with the medium range forecasting. So forecasting models have basically are divided into three components. So there's the nowcasting range, there's the medium term forecasting, and there's the climate forecasting. What we believe is the NWP, or the NWP models do perform better in the medium range forecast. In the nowcasting time frame, machine learning combined with NWP models potentially can have a better effect at improving the forecast. So the current state of the art in weather modeling is physics-based numerical weather models, which basically just take observations, any ground observations, atmospheric observations. They assimilate that data to estimate the current state of the world, which is data assimilation. They then do some physics simulation and rollouts, which is basically, they will estimate hundreds of potential future possibilities, which are ensembles. And then they do some sort of ensembling of these rollouts to basically get you a deterministic or a probabilistic forecast. So the problem with with this setup is it can basically take hours to run. So, from the time you get observations on the ground to the time you have a probabilistic forecast, it can be up to 6 hours, which is the case for HRES forecasting. HRES is a forecast provided by ECMWF. And so this is where we think machine learning can significantly help, because once you have a trained model, you can make the inference in seconds. So once you get the observations at your given current time, you can basically go directly to a probabilistic or a deterministic forecast in seconds or a few minutes. You don't really need to wait for hours for an NWP model to be ready to provide the forecast. Ideally, some of this is basically the reason we can see a huge boost in accuracy when we're providing real-time forecast to users. Basically, the forecast is as fresh as possible. So the input data that we are using into our models is from various data sources. So on the top left is the GOES satellite imagery. GOES is a geostationary satellite over North America and South America. There's various other satellite imagery like the Meteosats, Himawari, you have the Indian INSAT satellite as well. We're also using ground radar as an input wherever available. So the problem with ground radar is it's dense and has good coverage in places like the US and Europe, but it's extremely hard to acquire or have the data reasonably processed or be dense in other parts of the world. But wherever available, we are using ground radar as an input. We're also using iMerge data. So iMerge is a processed satellite data from NASA. So we're using that. We're also using HRES, which is NWP data. So even if the NWP data is stale, it comes in late, whatever we have available, we use that as an input.
Shreya, you have this bullet point, polar satellites measure precipitation, but at low resolution. Can you expand on that?
Yeah, so geostationary satellites have good resolution, like 1 kilometer resolution, which is pretty good. But the problem is, with the satellite observations, uh, it's from cloud tops, so you don't. It's very hard to see through the cloud tops to actually estimate what might be happening on the ground. So that's one inherent, I guess, downside of using satellite data that, it's very hard to estimate what's actually happening, to see through the clouds and know what's happening on the surface. Sorry, was that your question?
Question was, you're saying polar satellites actually can see precipitation.
Right.
Is that true? What does that mean?
So polar satellites, basically, again, they're like radar satellites. They can somewhat see, like they can better estimate through the clouds. From the microwave satellites that are there on board and the imaging satellite from the radar satellites, but the problem is they're still at 5 kilometer resolution.
Are there polar satellites available for India, for Indian rainfall?
So I would say there's the GPM DPR satellite, which is the best satellite that captures rainfall. The only problem again is, it's not taking a continuous instantaneous snapshot. Maybe and then the revisit rate over India might be low because it's continuously moving around the globe. It's basically this dual frequency precipitation radar satellite. Which is capturing precipitation over India, but at a low revisit rate.
Thank you.
Yeah. So for the various ground truths, you can have ground radar. As you can see, it's quite sparse. There's the dual frequency precipitation radar satellite, which is a polar orbiting satellite. So you're not getting an instantaneous snapshot of what's happening continuously, but when the satellite revisits over a region, you'll get a snapshot. So you can see here over India, we've only got like 2 or 3 revisits in I think like 2 or 3 days. So that's one hard thing about DPR satellites. And then the resolution is 5 kilometers. And then there's weather stations, which again, it's hard because the weather stations may not be well calibrated or could be very noisy around the globe. So these are various things that could be used as ground truth, basically. Ground radar that we have, at least over the US and other places, is very high resolution. So it's again 1 kilometers. DPR satellites are only 5-kilometer resolution. And yeah, but I think DPR satellites are a good way to estimate what might be happening in places we don't have ground radar. Okay. So that was the input and output ground truth data that we're using in our models. As for the loss function, so what we actually want to predict is we are trying to predict a probability of various precipitation rates. So what we do is we basically discretize the output, then have the model predict the discretized output. So the model actually predicts a probability, and the loss function we're using is sigmoid cross entropy. Yeah, so the prediction output is basically what is the probability of a given amount of precipitation at any specific location or time. So when we do predict, we're predicting on a grid. So, it's an evenly distributed grid points of various locations. And so, for the time horizon here is basically we're forecasting, so it's a nowcasting horizon. So from now up to say 24 hours, what is the probability of precipitation for any given rate? So there's various machine learning models that we can use for modeling. Starting off with very simplistic CNN style models. We can also use some unit style architectures. Unit style architectures, I would say, in general work very well. You might read a lot of papers about ML for weather modeling. You might like being used for various applications. And then inherently, you might notice that, unit cell models actually form a really good base for a lot of the architectures. And they do really well at predicting. So, if you're wondering, what is the kind of model I should start with? A unit style model is a reasonably good architecture to start with for your application. You can also use GANs, which will do better at, producing sharper forecasts. The model we've been using is called the MetNet model. The way we do this is basically we divide the area into many patches. So this purple box is kind of a patch over the globe. And then the input context is much larger than the target that we're predicting, because for nowcasting, basically, it's good for the target area to actually know what's happening around that target area. So, we have a larger input context and a smaller target area. The model itself, again, there's some unit embedded into the architecture itself, but it's doing various things, again, with convolutions. Dilation was another important aspect of this model. just because we wanted to again see a bigger field of view. We're doing some lead time embedding. Basically, what that means is, the model is not predicting, the model is basically taking the lead time to predict that as another input. So it's embedded. We're doing some cropping, tiling. There's various things going on here, but at the heart of it, a lot of the architecture can just be built on top of like simple CNN models or UNet architectures. And then we have the model is outputting probabilistic values. So what we actually do to go from probabilistic to deterministic values is we try and determine optimal thresholds. Thresholds to basically convert the probability into values of rain or no rain or heavy or light rain. These thresholds are not like, very simplistically, one could just apply a threshold of 0.5, but that's not necessarily true, that will be the most optimal threshold. In general, we're also trying to optimize this metric called critical success index. So we try and determine probability thresholds that can optimize for that specific metric. So this was just visualizing the output for one timestamp over the US. So on the bottom, where basically it's just you might see some gradients. It's the model is capturing probabilities, and then on the top is the ground truth. One thing you might notice is ML models in general have a tendency to blur out the output. So it's not as sharp as what NWP models might produce or what your ground truth might look like. This is one inherent downside of using ML models, especially if you're just going to use log functions like MSE or sigmoid cross entropy. And then there are ways we can do, there are ways to sharpen the output either in a post-processing setup or inherently through loss functions. Just to show one result from the model. So ENS is basically an ensemble that's output by ECMWS. And so it's basically, it can be ensemble to produce probabilistic outputs again. So we are comparing the probabilistic output of our model against ENS. And so CRPS is continuous ranked probability score. The lower, the better. So what we show here is that our model can outperform ENS at the first 24 hours. For evaluating the model, we use various metrics. A lot of these are based on, are based on classification scores. So F1 score and critical success index, basically, they determine, how well you're doing at predicting the true positives as compared to, your ratio of all the false positives or false negatives. Continuous ranked probability score and Brio score basically take your probabilistic output and kind of, it's kind of a mean squared error applied to your probabilistic output. And so CRPS just accumulates that is the predicted cumulative density function over various precipitation rates. Frequency bias basically measures the tendency of the forecast to overpredict or underpredict rainfall. I think that's an important one because sometimes the model might severely overpredict to improve certain metrics or might be severely underpredicting. And especially for precipitation, just because the skew of rainfall is so high, the models tend to sometimes severely underpredict or overpredict. It's a good measure to use. This is looking at another output from our model. On the top is the ENS model. The ground truth is in the middle, and then at the bottom is our MetNet model. You can also see, that it's a very smooth moving forecast. It's again because machine learning models can be trained, and then in real time the inference is very quick. We can actually forecast at uh, at a much higher temporal frequency than NWP-based models, which can, predict probably only hourly. And so, the movement of the forecast itself won't be as smooth as what you can expect out of ML models. Um, again, went through this. Basically, ML models have quick real-time inference. So, for a physics-based model to gather all the data, to do all the physics-based modeling, ensembling, and thresholding, it can be up to like range from an hour to up to 6 hours to get a reasonable output. And basically, 6 hour time range, it's gone past the nowcasting time range already. And for MetNet, once we have the model trained, like the inference is in seconds.
Shreya, in your quality of prediction that you're getting, can you attribute it to how much is from radar, how much is from satellite information, or from other sources?
Yeah, that's a good question. In fact, I was going to get into some interpretability next. Um, so exactly what Professor Sandeep asked. Basically, determining what is an input, what is an important input into the model is important to actually know, that, if we're going to apply this model to another region, what kind of inputs should we be trying to get? And, what kind of an accuracy drop do we see with, say, like missing radar or um, a drop in like NWP, like, the way NWP forecast. So we tried to do interpretability of our models using this technique called integrated gradients. What that is doing is it's basically um, it's taking the gradient of the model, uh, and then you perturb the inputs slightly. As you perturb the input slightly, basically you will see the net output is affected. And so when you integrate that over like many perturbations, you'll see, which variables basically had the highest effect. Um, so here's looking at basically I've cherry picked some plots to show. I can dive deeper into like various other variables. But what we really noticed was that when we include this variable called absolute vorticity from NWP models in our data, that variable actually has a significant uh, contribution to our models. And that variable, so we have variables from different atmospheric levels at different HPAs. So when we include that data from the higher atmospheric levels, so from 200 to say like 500 atmospheric pressure levels, um, that actually had a significant that gave a significant boost to the accuracy of our models. There's also this quasi-geostrophic theory in weather modeling. So this effect was consistent with that, which is saying, the model is learning some information from, is learning some physics itself.
So I had a question.
Mhm.
So talk about the interpretability that you would vary the variables slightly to
Mhm.
just figure out if variables are having water path. How does that scale with increasing variables? Because typically in a machine learning network, you might have a lot of input variables, and I'm assuming this might be something that perform in 2 or 3 to the power n, where n is the number of variables, because you might take some number of measurements above and below this to what's calling
Right. So the good thing about integrated gradients was, we don't have to perturb each variable separately. Um, so we could perturb basically uh, all the inputs together, and that would affect basically the uh, uh, yeah, like I can go more into integrated gradients like later as well. But basically, the way we were doing this was basically perturbing all the inputs together.
And how do you get to
Um,
know when you cause the output?
So we can basically like get the gradients of the model associated per variable. Like when you like from the model architecture itself, you can extract like the initial connections of the input into the model. You can extract the gradient. Yeah, you can like in the code basically you can get it per variable. So like I guess what will happen is when we like if any let's say if 100 of the variables did not have any effect on the model, then the gradient associated with just those variables would be close to zero. Um, um, yeah, it's hard for me to explain, I guess, verbally, but in code we can get a gradient per variable.
Thank you.
Okay, so here we're looking at attribution for some other variables. So we're looking at temperature, dew point temperature, relative humidity, and specific humidity. So we can see, all of these variables did have some effect on the model, but mostly for lower atmospheric levels. So, closer to the surface of the ground. We also tried to do, understand spatially how much of the, spatial input has an effect on the output. So on the bottom is basically just looking at the integrated gradients again. And so the darker blue indicates, what was important to the model. So, it's not fully clear what's going on here. Like that's another hard thing about doing interpretability is that, even when you get results, it might be really hard to understand the results itself. So, I guess I'm presenting this here for like, what kind of outputs you might get, but then actually interpreting those outputs can also be hard. So, we have some spatial maps here looking at, um, which pixels were actually important to the model when we made the prediction on the top. Um, but at least as computer scientists, it's very hard to know. So, one thing I would suggest is, definitely get like weather experts to work with you or meteorologists to work with you, who can explain more about, how different spatial maps might be, interpretability maps might be influencing the outcome. Um, so for potential future research directions, one of the things I spoke about was like the blurriness aspect. So ML models do tend to be blurry. They tend to blur out the output itself. If you just use things like MSE, the effect is even more pronounced because what that will do is it will have a damping effect on the extreme precipitation rates. And the forecast will be even more smooth because MSE tries to average things out. So, with sigmoid cross entropy, you can at least do a little better. But it still doesn't fully solve the problem of like a blurry forecast in general. So how do we make it sharper? I would encourage everyone to look at things like spectral losses that can help, and just maybe playing around with various kind of losses. Can machine learning the one of the really challenging problems is again predicting extreme weather well. And the problem is, there tends to be not enough data for extreme events, which also affects the accuracy of the ML models itself. Or, again, the kind of loss function you use can affect the model's accuracy for predicting extreme events well. So, just focusing on extreme weather is another important avenue. And then forecasting basically when we don't have enough observations for a given region. So for observations for regions around the globe where, say like places like Africa where you don't have good weather radar, or, over the tropics where basically, in a lot of places we don't have good coverage of radar. Satellites can help cover some of those gaps, but the problem again is, can they really see through cloud tops? Um, for like focusing on some of these regions, observation sparse regions is an important avenue again.
I had a
Okay.
question.
Mhm.
The last part, how do you target observations for sequence? Has there been any work done in, let's say, using some sort of foundation model that trained on regions with observation and sequence, and then trying to transfer it on into observations for regions so that you can at least get some sort of understanding of whether with the foundation model and then try to tune it to observations for regions? Has there been work
Yeah,
done?
that's exactly where I think foundation models can actually be really helpful. Um, yeah, so basically, you find some sort of common embeddings over regions where there is a lot of data, over dense data-rich regions. You build a foundation model and then ideally apply it to data sparse regions. So I think that's actually the place where I think it can be most helpful. Um, but it can be still hard, in the sense, the training amount of training data you need to train over can be uh, should be ideally large to make like some inferences across different data sets.
Shreya, one more question for you. When you had this MedNet one, it was 8 hours of nowcasting, and now you're going up to 24 hours. What extra information is making you, make better predictions for this? Then what are you able to learn?
Yeah. So I guess in terms of weather information that we added, adding weather stations helped somewhat. But again, the problem is when you add weather stations, you can do well over countries like US. It's really hard to get good quality weather station or rain gauge data over places like India. Another thing is architecture improvements. So we've tried to include things like transformers into the model setup itself. That again helped a lot. Another thing is increasing the context size. So, basically the model should be able to view further and further out. As you're going to increase the time range, at some point, ideally, the model should be able to see the entire globe in a single input. Um, you know, there might be something that's coming from Asia that goes over the Pacific. Yeah, so increasing the context size.
Context size only spatially, or also like you want to see the whole globe, but also multiple time periods in backward.
I would say more spatially. Um, so, basically this blue area is our context that we're providing as an input, and our target is a smaller area. So, increasing spatially this blue area. Um, I would say that, we try to incorporate more timestamps, more historical timestamps into the model. But that is not something that had a significant effect in improving the accuracy.
By weather stations, you mean simply places where they are measuring the amount of rainfall, the temperature.
Yes. Yeah, but then, again, I would say it's a very US specific improvement that you will see, just because the density of weather stations is like, so this is the weather station network over the US. It's much higher, and then the gauges are also well calibrated. Um, which unfortunately, I have not seen a lot in India.
Have you done Africa or India forecasting, and how much worse it is compared to US and then?
Yeah. So, that's basically what we're currently working on is, how do we forecast well in places like Africa and India? Um, in general, the performance in observation sparse regions will be lower than what you can get in, say, the US or Europe. It's primarily, again, because of the availability of ground radar. But I think satellites can again are improving the accuracy of the model quite well.
So how are you
Mhm.
output?
Sorry, the voice is getting quite cut. I'm unable to hear.
Can you hear me now?
Yeah.
My question was, using uh, the outputs from the numerical weather prediction models as a baseline along with the ground truths we have learned.
I don't know if it's like a mic connection issue, but maybe someone from the front can repeat the question.
Is it better now?
Yeah, slightly better.
My question was, how are you using output numerical weather prediction models together with the ground truths to make a prediction? In what role has the numerical weather prediction models has to play as a base?
Yeah, so if I understand the question correctly, it's, what is the role of using NWP as an input into the model itself?
That's correct.
Yeah. So I would say NWP actually has been one of the most important variables as an input. So basically from NWP, we're using many different kind of variables as an input. So like absolute vorticity, temperature, humidity, and also at different atmospheric levels. I would say that has been, that has given the models the biggest boost. Also, in some sense, what we do is we basically incorporate the forecast of the NWP model itself into our model. So in some ways, we are post-processing that forecast.
I heard you say the models take 6 hours to come out. So how do you?
Yeah, so what we do is we basically so let's say we're trying to make a 1 hour forecast. We take the 7 hour forecast from the NWP model. So because the model is going to be 6 hours delayed anyway, like we're not going to get the 1 hour forecast from NWP in time. But what we will have is we will have the forecast from from 6 hours ago. So the 7 hour forecast is used as an input.
It's just directly used. So you're saying you'll use this 7 hour forecast and maybe you'll use some other reanalysis variables as input to your model.
Exactly. Yeah.
That goes a long way.
Yeah.
Any other? Yeah, there's some more questions. Can you hear me?
Yeah.
Regarding interpreting neural networks, you mentioned how you can explore the relationship between the input variables and the output. So what more can be done in interpreting neural networks specifically for web? Like figuring out like the relationship between input variables or like seeing whether the network is actually learning physical laws or whether
Sorry, can you repeat the last part again? The last question.
yeah, the last part was like what more can be done in interpreting neural networks for web? Like
What more have we done incorporating neural networks for?
interpreting a neural networks for web.
Oh, interpreting the neural networks. Yeah, so we tried integrated gradients. Um, yeah. I would say uh, there's I had another paper called Rain Check. It's basically, it actually talks about a few other things. There's basically, a lot of work on gradients itself. So there's a grad camp paper. You can look at, the technique from this grad camp. It's like a gradient-based localization network. I would say these are the mainly two things I looked at. It's not something I spent a lot of time doing, probably like 6 months. Um, yeah, but I think we could do more, but it would definitely require spending a lot more time. Yeah, unfortunately, I don't have a good answer. Like it's not something, we dived a lot into.
I have one more question. Can you hear me?
Yeah.
So
Google's put out quite a few weather and climate models recently. Obviously there's MetNet, but there's also been GraphCast and there's
Mhm,
now GCM.
mhm.
So could you talk a little bit about how the different approaches that have been taken have yielded different results and what you've learned over the years in terms of, what matters in terms of different time horizon forecasting, what matters for NW integration also.
Yeah. Um, so I would say, so all the models had very different focuses. So like GraphCast was very specifically focused on medium range forecasting. Also, so was Neural GCM. So, before you, like I would say, when you pick a specific application, it's good to decide on, what time horizons, spatial horizons you'll be working with. So, they had also much lower spatial and temporal resolution. So I believe it's like 0.25 degrees, like which is like 25 kilometers by 25 kilometers. Um, Basically what that affects is, how much data you can fit into memory. Like it would become really, really hard to do medium range forecasting at the 1 kilometer spatial resolution. Or for nowcasting range, the temporal frequency, being able to predict every 5 minutes is important, which is not really critical for medium range forecasting. The users don't have to know what's going to happen 3 days, 4 hours, and 5 minutes later. Um, so those are some of the differences in the sense that, they were working with uh, they decided that they wanted to focus on medium range forecasting. So then they were working with the data sets that, that are also coarser in resolution but can fit into memory. For medium range forecasting, again, you need to fit the entire globe pretty much into your model, for predicting any target area. So again, being able to fit the entire globe at the 1 kilometer resolution would be really hard when you're training these models. So, um, and then for neural GCM, it's a physics-based model. Um, and so, you know, it's obviously doing the best. Um, but the focus again was, um, how do we incorporate physics into the model? So as a learning, I would say, um, we can build a lot of models, but being very focused about, the exact outcome we want to achieve or the exact application that we're targeting can help a lot because, you can have weather data. There's lots and lots of weather data to work with. If you start looking out for data, you'll just come across lots of it. So being able to, filter the exact data sets you want to work with, what resolution you are targeting. So, filtering out your data sets again to, the the resolution that matters to you helps a lot. Um, Incorporating physics and understanding the outcomes again, I think is important. So, if your goal is to have like, sharper forecasts, which is basically the case for things like GraphCast or Neural GCM, um, then, I think in some sense you do need to incorporate some sort of physics or, sharpness metrics into your evaluation strategies. So um, I would say identifying first the output or application area will help you decide. Um, it will help you decide better, what kind of inputs and models to work with.
And so, as compute keeps increasing and as we understand these models more and more, do you think we're going to see a consolidation of these different sorts of focus models into one single sort of agglomeration? Or do you think different focus projects with different ideas is the way to go?
Uh, it's a really hard question to answer. Um, yeah, I think uh, I think focused models it will be in the short term, it will be easier to achieve good results with focused models. Foundation models can take years to develop. So, it really depends on, what you know, are you okay waiting, say, a couple of years for results from foundation models, from gathering all that data, cleaning it up, you know, potentially seeing failures along the way? Or, if you have a very specific output, let's say in weather modeling for agriculture or like, forecasting for, when should the farmers be harvesting. Sometimes very like a dedicated model just for that, I think can yield results quicker. Yeah. And then, combining a lot of models for, very many applications, it can take a lot of infrastructure also. The training hardware, you'll need a lot of it. So I would say it also depends on, kind of, how much capacity do you have? How much training hardware access do you have? And you can achieve really good results in, just with by training on CPUs or GPUs actually, just with a smaller dedicated model. Like you don't, I would say it's an like the hardware constraint should not restrict you from being able to, you know, work for the specific application you have in mind. And so, it's okay if you build small focused models.
Further questions? So then, Bhavesh, you had a question, right?
Yeah, I wrote it in the chat. I thought, yeah, but thanks, Shreya. My question was, do you think using an ensemble model helps like with ML? Are you using ensemble in your models?
Yeah, so we're not really directly inputting ensemble data into the model. Yeah, we're just using the HRS forecasts, or in the US, there's a HRRR model, HER model. I believe even IMD has a HER model now. Yeah, but we're not using ensembles as an input. It's a good idea. I guess it's just something we haven't got into. It also means, you're taking all the different ensemble outputs as an input, which can increase the data by a lot.
No, I meant using ensemble of models. So one is the output of these models you are using, and the other is the model itself. You are using the deep models, and can there be a ensemble of models, and then you sort of give a prediction based upon some mechanism ensembles.
Yeah, I actually think that's a really good idea. So, having an ensemble of models and doing a post-processing setup is actually what a lot of agencies or companies do. And I think eventually for medium range forecasting, especially, I think that is the way to go. Because, a lot of different models will have different strengths. And ideally, putting together an ensemble of models and then, post-processing the output from those models will likely give you like even better accuracies. So I would say that's something, we're kind of already doing for medium range forecasting. Not through GraphCast or neural GCM, but for from other things, we're already thinking about using an ensemble of outputs now that we have all of these different models. I think that will basically give you a better model.
Right. Yeah. Thank you.
Okay, so if there are no more questions, thank you so much, Shreya. We really enjoyed the presentation. Thank you.
Yeah, thanks all for having me here.
All right, have a good day. Okay, guys, so we'll all meet tomorrow at 9:30 in the morning. Mike will not. Oh. All right. Guys, can you hear me? Okay, so we'll all meet tomorrow morning at 9:30 a.m. We'll start by a presentation by W. Schneider.
I think tomorrow we should ask IT for a better laptop, or if possible, get a standalone mic. Yeah, because I think the first presentation is not that bad.
Yeah.
I think it might just be better to have some external mic plugged in.
Right. So, can you ask them?
Does IT give mics?
So two things to make. First, let's tell Tapio about the new address, the Zoom address, the second day, not the first day. And secondly, can we ask IT folks to just give a better laptop, with the mic which works, yeah. And just be around, I guess. They should not be.
That's true. I think for just a standalone mic could also work.
Yeah, it should be fine. I'll ask them.
Because I don't think they give and this is the best laptop they have.
I do think.
Is that right?
I think this is the best one they have. They don't give this to
So it's
students.
also that the regular laptops don't have, they lend them out to you. And so the ones they left with are usually the worst ones.
There's also one question. You talk where I had to be for the end. Over there, you asked a question about, when they use CNN, so they directly just use CNN to do extraction.
This is for the satellite, yeah.
This was what was the,
No, that I think it was one of your voice was so bad. It did not make sense. I could have asked Shreya also. I am worried because